So, agenda for today. So, a lot of my research has been on Android security, and I'll tell you the reason why I have targeted Android. The next slide. So, we will talk about the same only policy. So, whenever you go for an interview, normally, whenever you get interviewed in a company like Google, Facebook, Dropbox, so on and so forth, the first question that they will ask you if you're from the application is what the same only policy is. Because same only policy is the most important security mechanism that is implemented by browser vendors, and it is an imperfect one. We will see what the same only policy is. Then we'll talk about typical case of vulnerability that I found. A same only policy which was elevated to a remote code execution. By utilizing it, we were able to achieve a remote code execution on an Android device by utilizing a same only policy. We'll talk about cross-scheme data exposure attacks. This is cross-scheme data exposure. This is a term that I personally coined for a set of same only policy bypass attacks. We will talk about browser cookie theft attacks. We'll talk about spoofing attacks. We'll talk about Charset Inheritance attacks. We'll talk about CSP bypasses and the common issues with Android patch management. Yeah, so what's not covered? I'm not going to cover memory corruption. We did the experts because number one, they are not. It's not my area of expertise. Number two is that it's very difficult to basically create and develop exploit for Android. Work on simultaneously work on all the Android versions that could work on simulators, so on and so forth. So there are a lot of issues. Especially when we are talking about memory corruption. And that is the reason that recently we have seen stage fright, which was a vulnerability in one of the Android's core libraries. But we are yet to see a working exploit, a working POC that could affect all of the Android version. Now the same is the case with Chrome, and the same is the case with operating system because of the mitigations such as ASLR and DAP and so on and so forth that have been developed over the years. It's very difficult for someone to form a working memory corruption exploit that is able to work every time. And that is the reason why we will not talk about memory corruption vulnerabilities. So yeah, why Android? Android has 82% of total market share. And I'm talking from 2015. Now I think it's more than like 87%. So we have 82.8%. This is for 2015 quarter 2. That we have 82.8% Android and 13.9% iOS, and followed by Windows Phone and BlackBerry OS, which is of course dying because now they have shifted towards Android as well. And the version distribution. So as you can see that. Android gingerbread. Surprisingly, it's very good, but it still boasts like 3.8% of all the users for Android. We still have some users for Jelly Bean. Though Jelly Bean is pretty good now, we have Lollipop and Marshmallow 6.1. But due to how Android patch management works, the exploits that I primarily found were in 2014 and 2015, but they still, till date, 30 to 40% of the devices are still vulnerable to these exploits due to the way how Android patch management works. So these all are not the sponsors of my talk. These are the browsers in which I have found vulnerabilities. A lot of them have responded, a lot of them have not responded. My recent work was in Google Chrome, and which went into Google Chrome, Firefox browser. It was a spoofing bug. So it was just one spoofing bug, Android spoofing, which as per Google it holds medium risk. They categorize it under medium risk, and they awarded me $5,000 for that single bug. We'll talk about. So yeah, so testing methodology, a lot of people ask like how I found so many of these browser bugs. So they ask me whether you have used Accunatics, whether you have used NetSparker, or maybe Nicto. But the problem is that if you Google, you would find no single automated scanner for browser bugs. And even source code review is very, very difficult for the browser bugs, because consider browsers are written in C++. and of course they interact with operating systems, so they utilize their code library. So it's very, very difficult to basically analyze millions and millions of lines of code. And browsers are nowadays extremely complex. Nowadays they are as complex as operating systems. So due to the fact that our browsers are constructed of many different layers, and we have like browser especially DOM is a complete mess. We are complicating JavaScript, we complicating DOM, and on top of that we have added different plugins. We have added applet, Java applet, we have added Flash, so on and so forth. So browsers are very complex. So yeah, so scanner cannot be used like Unix and NetSpark, they cannot be used to find browser bugs. Here. And as a part of my research, I have developed this test suite to make things easier for you. Now, this test suite basically consists more than 50 plus test cases that I have. Some of them I took from different researchers and different proof of concepts, and others I have personally developed. I developed this test case and basically I applied it across the top 100 Google Play, top 100 browsers present in Google Play Store, and I found more than 50% of them are vulnerable to one of these bypasses. So yeah, if you want to do some research, further research, what you can do is you can utilize the same test case, same SOP bypass toolkit, and you can utilize it against iOS. You can utilize it against different browsers. So yeah, the key to bug bounty still is to basically look into the places where others haven't looked into. So for instance, Yandex browser. How many of you have heard about Yandex? It's a Russian company, right? It had a bug bounty program. So a lot of people had forgot, and a lot of people were busy with HackerOne and Bugcrowd while I was still hunting with Yandex and Avast and other bug bounty, and AT&T, other bug bounty programs which are temporarily forgotten. So the key here is to tap the hidden treasure, the forgotten treasure rather. So yeah, these are the references for the testing. I'll share the slide. I have basically modified my Black Hat talk, and in this talk, because Black Hat I just had 25 minutes to talk about these topics, but I have modified the slide, and the modified version of this slide will be uploaded on Null after this talk. Typically, this is how browser works. Every single browser that you see, because right now we have three main browsers. We have the Chrome browser, we have Firefox, and we have Internet Explorer. That's it. Because every single browser that you see is basically fork of these. So every single browser has these main components. We have the user interface. What user interface is? It's basically your back button, your forward button, your refresh button, your address bar. So our user interface. This is back button, forward button, refresh button. Anything you see in the browser apart from the browser window itself is part of your user interface. And then we have the rendering engine. Now rendering engine is a very complex part. This is basically the core of the browser. Every browser has its rendering engine. You might have heard about WebKit. WebKit is a rendering engine for Google Chrome and Safari. Now they have made a different fork, which is Blink. They have Google took WebKit and modified it as per its needs. So before Google Chrome and Safari both were using WebKit. So a bug that was found in Google Chrome would also affect, if the bug was found in the rendering engine part, it would also affect Safari as well, because they both were using the same rendering engine. Now between user interface UI and rendering engine, we have browser engine. Now, what browser engine does is it simply connects user interface to rendering engine. need to understand that our browser is constructed of different layers. Right? We have the networking part. Now, what networking part does is it simply utilizes underlying operating system libraries to basically perform DNS requests. So when you type google.com, the networking part would do what? It would send a DNS query and return the IP address, resolve to its corresponding IP address. So this is what's done by networking part. We have JavaScript interpreter, very important part of modern browsers. So rendering engine, what it does is it basically, simply put, what does it simply takes your HTML, it takes your CSS, and it basically paints everything on your screen. So whatever you see on the screen is basically done by rendering engine. It takes your HTML and then construct a DOM tree and then construct a render. It's very, very complicated, but the high level is that it takes your HTML, it takes your CSS, and basically paints what you see on the browser. UI backend, it's basically used to draw rectangles and squares and size and different things. It's not a very important part, but important is rendering engine. And yeah, the JavaScript interpreter, different browsers have their own different JavaScript interpreters. And such as we have V8 for Chrome, we have Spider20 for Firefox, so on and so forth. Then we have this data persistence layer. So browsers also have to save some data. So for example, when you log into a web page and you click remember me, so browser stores that piece, browser remembers it via your cookies, which are basically stored on the client side. So this is the data persistence layer. So yeah, same origin policy. The thing is that the thing about same origin policy is that it's a policy that both developers and attackers hate. That's one of the very few policies, a security policy that developers hate as well and attackers hate as well. But at the same time, it's not a consistent policy. We'll see what this means. So the simplest analogy, the example that I can come up for explaining same origin policy is that we all use browsers every day. So I mean, most of the time I use a computer, my browser is open, and I think the same is the case with every single one of you. Because browser now itself is an operating system. And of course, we have different tabs open in our browser. So let's say we have email.com open in one tab. And then we have gmail.com open in another tab. Now we trust our browser, we trust Chrome that email.com and gmail.com would not exchange the data behind the back. We trust it. So if there was no same origin policy, all you could have done is that email.com would have easily requested content and retrieve your emails from gmail.com. Same origin policy was basically developed in 1995, between 1995 and 1996 by Netscape, when they basically invented frames, when they invented iframes. The concept of iframe, the frame is basically almost 20 years back, when the web was in its initial phases. And then they realized that if a website can frame another website, and we all use iframes, right? They developed this, they said that if a website can frame another website, and then basically retrieve the content out of that frame, this would mean it would be a very big security breach, right? Because I can simply ask you to go to email.com and email.com would retrieve data from every single tab. So they came up with this same origin policy. Now, since they came up with this same origin policy, every browser had its own implementation of same origin policy. Every browser, there was a standard set by W3C, but it was so vague that every browser thought to come up with its own same origin policy. So yeah, what same origin policy means in more technical terms. Now we are basically diving into the topic. This was background. Now we will get into the technical part. So yeah, the same origin policy, as it states, that restricts communication of active content to object that share the same origin, which means that a website, we we have different origins. We'll talk what origin is. So a malicious JavaScript or a script, a content present on one origin, say xyz.com, should not be able to access content of gmail.com or any other domain. So this is what the same origin policy is. So what exactly is an origin? So how it checks for origin? So let's say we have a website http www.example.com 8080. Scheme is http, hostname is example.com, and the code is 8080. So the origin is a combination of scheme plus hostname plus code. So let's say http www.example.com:8080 tries to access http www.example.com:8081. It would say code mismatch. So 8080, the script present at 8080 will not be able to access 8081. And similarly, if script present at example.com would try to access subdomain.example.com, since the hostname would mismatch, it would not allow it to query. The same is the case with scheme. If it's FTP, if it's HTTPS, if one of these three elements mismatch, the same origin policy would come into play and it would trigger an exception. And that is the reason why developers hate it. Hackers hate it because, you know, if there was no same origin policy, I would have just asked you to click a link and that's it. You know, I would have retrieved all the content from gmail.com, facebook.com. I'll show you then how I was able to do that with request. Right. So, time for quick exercise. Origin 1 and origin 2 are the same origin? How many of you say they are same origin? Raise your hands. And how many of you say they are not same origin? So what are the rest doing? Yes and no? Yeah. They are same origin. If you see HTTP, scheme is same. And store.example.com is same. Hosting is same. The path doesn't matter.
HTTP.
It may be page.html, it may be home/newpage.html. So since scheme, hostname and ports are same, they both are same origin, right? So how about this? How many of you say they both are same origin?
No.
And how many of you say they are not same origin?
Same origin.
They are same origin?
No.
How many of you say they are same origin? They are same origin? Same origin?
Only one.
No. Because as you can see that there is no mismatch. We have use.example.com with store.example.com. So if one of these three elements mismatch, the elements would not be on the same origin.
See, you said hostname, right?
Yeah. Both of them are different host names.
Because the subdomain.
Because the subdomain, right?
But
It's the subdomain.
no. Host name, when I say host name, it means that this has to be unique. This has to be unique now. Under same origin policy.
Instead of hostname, you should say FQDN.
Okay, FQDN. But typically we call it host name. When we try to define same origin policy as per specs. The reason which I call it host name.
And the confusion is because whenever the cookies are set in the browser, it says start.abc.com. That's why all the subdomains take that cookie.
Now thing is,
but that's wrong.
you're right. The cookies are not subject to same origin policy because cookies are older than same origin policy. Same origin policy was introduced in 1986. So you know that the cookie can be set to scope to a page or directory, but this is not the case with same origin policy. So cookies are an exception to same origin policy. If I can put it that way. We'll take questions later on. 1995. In 1995, cookies were invented. In 1996, same origin policy was invented. So cookies are way older than same origin policy, and that is the reason why cookies are not subject to same origin policy. And that is the reason why I said, this subject is pretty confusing, but I am trying my best to So are they both same origin?
No.
No? Yes or no?
No.
And
It's on
this
a
is
different
where another
port.
exception comes.
It's on a different port.
For I and text.
Yes, for I. So the Internet Explorer, as I said, every single browser has implemented same policy in its own way. So, other browsers, they say, okay, host name, the scheme, the host name, FQDM, or port, they are different, so they are not same origin. They say no. So Chrome and Firefox thing, they are not same origin, right? But when we talk about Internet Explorer, as per its same origin policy, does not consider 8080. It does not take port name into consideration when deciding the same origin policy. It only decides it on basis of scheme and host name. That's it. Origin 1 and origin 2. Are they same origin? Yes or no? How many say they are same origin? And how many of you say they are not same origin? They are not same origin. They are not same origin. How many of you say they are not same origin?
The first example.
The last example finally. I'm trying to explain the inconsistency of this policy. That's the reason why I say because they both are same origin. Now how in the hell they are same origin? So the thing is that all of these pseudo protocols, or about.blank, we have data URI, we have JavaScript URI, they are on the same origin. This is what the policy states. So if you print w.open about.blank, if you open about.blank in a new window and try to write to that window, it will write to that window. Right? The same you can do with data URI. And that's the reason why many of the phishing pages nowadays use data URI. Yeah. So a bit more technical part. Simple XML HTTP request. Save it as X for open. I forgot to put S over here. So what it's doing is simply querying gmail.com. It's simply querying gmail.com and retrieving the response. That's it. Now, under same origin policy, as you can see, that Chrome has a region exception. Says that XML request cannot load gmail.com, no access control allow origin header expression on the request resource. Origin null is therefore not allowed to access. So you can see that output.jsp.com is a different origin than gmail.com. So same origin policy would not allow output.jsp.com or any host name, any null origin to basically access gmail.com or any other origin.
So going back on the previous example, if I'm on about.blank and I open my developer toolbar and I try to run that same task, the same exact script, would you be able to fetch content that's as we say from gmail.com? Gmail.com also.
Coming in.
So you have about.blank in one page and then you have gmail.com open in another page. Now because the browser has inconsistencies in terms of defining the origin, if I try to run an Ajax
if you do window.open from gmail.com, so then about.blank will be able to access gmail.com. It's not like if you open about.blank and
yeah, because a lot of times in Internet Explorer you have a default page, you could set it to about.blank. So
Yeah.
you are saying that only if about.blank was triggered from gmail.com.
it's because it basically inherits the origin that it's requested from. So about.blank data, they basically inherit the origin from where they are requested.
It's not really vulnerability, right? Because no one is in control of
About.blank. Yeah, but US owns 13 root DNS, 11 out of 13 root DNS servers, so they are in the control of the internet. Anyways, severity of a SOP bypass. So I'm trying to basically explain the severity of a same origin policy bypass. In October 2012, Firefox released this statement where they said that Firefox 16 has been temporarily removed from the current installer page. So Firefox 16 was released. It fixed 14 different memory corruption vulnerabilities. Out of them, 11 were critical memory corruption and 3 were high risk memory corruption. And then when they released Firefox 16, Gareth Hayes found the same origin policy bypass. and it was so trivial to exploit that they basically removed Firefox 16 from the installer page and asked your user to use Firefox 15, which was itself vulnerable to 14 different memory corruption vulnerabilities. Due to the fact, now who can tell me why? Of course, we have very good engineers, security engineers in Firefox, who would trade 14 memory corruption vulnerabilities with one single policy bypass.
The difficulty to exploit.
Yes.
The difficulty to exploit.
Yes. The difficulty to exploit. So, if anyone has worked with memory corruption exploit, he or she would know that memory corruption has this attack probability. They work sometime and they don't work sometime. There are different factors that we have to take into account. But same policy is an API abuse. All of the same policies are typically an API abuse and layer mismatch. And they do not require an attack probability, and they have to work every single time. And they are very trivial to exploit. There are two types of same policy bypass. We have CSP bypass by design, and we have CSP bypass by implementation. In Java, a shared hosting means there is the same policy bypass. So Java has this was basically fixed in 1.6.7, but before that, this was a vulnerability that was found by Stefano Di Paolo. We found that two hosts are considered equivalent if both host names can be resolved using the same IP addresses. So example.com and example.net, if they both share the same IP address, they are both same origin. Now this is a disaster in case of a shared hosting environment, where basically you are hosting hundreds and thousands of domains on a single server. This means that every single server, every single website, so if you want to hack a website, all you can do is you can contact the hosting provider and say that I need my domain on this particular server, and then basically you can trick the users. So this is by design, right? Now I'll talk about SOP bypass by implementation. This was found in Internet Explorer 6 by Gareth Hayes. Now we found that all you have to do to bypass same policy is basically put document.domain to target.com and basically simply alert document.domain. If you try to do this in modern browser, it would trigger an exception. It would say that it's not a suffix of target.com, and that for that very reason it would not be able to set the origin. So document.domain property basically is used to set a host name. Just like location.hostname is another property that can be utilized. So basically what it does is tries to set, so it's on event.com, it tries to set document.domain to target.com, and then when it alert document.domain, it points to target.com. Very easy and a simple explanation of same policy bypass by implementation. Now, so this was found in 2007. This was the same policy bypass in Firefox. So the location.hostname, we simply set location.hostname to email.com/null, followed by www.example.com. Now can you tell me, is this email.com or example.com? What would browser think?
Evil.com.
But it would be eventually processed in example.com.
No, if I try to run this code in modern browsers, what would browser think? Would it think example.com or email.com? No, example.com. Because it would basically consider this part as a subdomain. It would consider this part as a subdomain, that the domain is at the far right. If we look it from here. If you look it from here, then it's a different slide.
That might be considered as a dot because the subdomain will always be followed.
It's not considered as a dot basically. What happens is when you run it in Firefox, the vulnerability is one layer. I said our browser is constructed of different layers. So one layer, say for instance DNS, since basically DNS comes from all of our browser code is basically written in C++. DNS comes from the ASCII world. So in ASCII, and C, you can see that a null byte means string terminator. It means that you have to stop the execution. So one layer, so the DOM basically, when DOM tries to pass this, it basically ignores null byte and it thinks that the domain is example.com. But when it tries to request to this website, the DNS thinks that it's evil.com because it stops at null byte. So there is a layer mismatch between DNS and DOM. So this was the vulnerability. So it thought it was evil.com. So basically you can set www.gmail.com and evil.com, and it would basically be able to access whatever is present as a file. So they will actually fix the vulnerability by filtering out for these null byte characters. Because null byte has been a very big problem even in today's application, even still with PHP, because PHP itself comes from the world of C++. Null byte has been a very big problem. So now, since we are moving to higher abstraction layers, higher level of abstractions, we are of course trading performance. We do not have much of the null byte problem, but since browsers, a lot of components, they basically come from C++, and C in C++ and ASCII word it is considered as a string terminator. Now, as I said, all symbolic policy bypasses are similar in nature. Now, who can explain what this code is doing? Very similar.
Loading a website image.
Trying to make a main code to bring account.
Loading the main.com.
Is it could be called bing.com or evil.com?
Going by the one we didn't call main.com.
But why? This is recently released vulnerability by a guy who used to run a lot of access challenges. I don't remember his name. But see, cookie store, as I said, layer mismatch. So cookie store is that data persistent layer. If you go back, as I said, we have different layers in the browser. Data persistent. We have cookies over here. And the DNS, we are into the networking part. So, as the browser tries to parse this, the cookie store thinks that it's a subdomain of bing.com. So it thinks that the origin is bing.com, right? But since the DNS resolver, it comes from C++ code, it thinks it's evil.com as it stops at null byte. So basically, what you can do is you can load the target website into an image and before simply append it with null byte, and it would be considered as a same origin policy bypass. Simply because evil.com now is able to access and retrieve contents from bing.com and another origin. So my research with Android browsers, it has mostly been with Android browsers, and I have found like more than 5 different SOP bypasses, and especially in the WebView component of Android stock browsers and other different browsers present at Play Store. What is WebView? No Android developer will browser for the web.
You can load the website.
An application, if an application would like to embed something from the web page, you could simply use the WebView. That's it. And the WebView utilizes WebKit rendering engine, which is coded in C++. That's a very important thing to remember because almost all of the bypasses, many of the bypasses I've seen that null byte has been a key, and you see that how I utilized null byte to my advantage. At that time, a 4.4 KitKat was just released. So my symbolic policy bypass basically affected more than 80% of the internet traffic. So multiple Metasploit modules were created. We created basically me and Joe, we created 5 different Metasploit modules for exploiting it, for demonstrating this vulnerability. This is same policy bypass. Simply, we load RHA infosec into an iframe. And basically what we use is we use window.open function to execute JavaScript. And the browser confuses and simply execute the JavaScript due to this null byte. It simply executes the JavaScript into the context of RHA infosec. So whatever website you frame, basically when you append a null byte and with window.open function, it would basically execute into the concept of into the context of RHA infosec. Now one thing I would like to point over here is that all of the same policy bypasses you would see, most of them you would see with iframe tag, you would see it with window.open function, you would see it with post message calls. Due to the fact that of course you have to find functions that are utilized by a browser, that are utilized to interact between different domains. And that is where you can simply find same policy bypass. So yeah, as you can see that the domain is JSBin, right? That's upon executing this code. And the page at RHA-infosec says document.domain property, that which is www.rhainfosec.com. So JSBin, the JavaScript at JSBin is able to access property of rhainfosec.com, which is a different origin, which is clearly a same origin policy. So yeah, I have a video demonstration. So this video would demonstrate a Metasploit module that me and Joe Minix wrote in order to exploit this very same origin policy bypass. So let's start. I said, of course, widely aware of the basic syntax. What we are simply doing is we are loading the auxiliary module. So you can see from here this is an emulator, and in an emulator I have Facebook open. I have logged into my Facebook and I have messaged someone CSP Bypass. This is a message that I have sent to someone. So since Facebook uses extreme options, you utilize this method bypass underscore xfo, which uses window.open function to exploit this vulnerability. And we set the target URL to mw.com. And now our script is running on a different origin, which is 192.168.8.102 port 8080. Now this is a different origin, and Facebook is a different origin. Now see how this works. As soon as I browse this link, now this can be a link that can be sent via Facebook or via an email. So as soon as I click it, it has grabbed the response. Same origin policy has been bypassed, and all the response has been stored into this text file. Now as soon as I open this text file, you can see that all the content has been retrieved, including the C underscore user cookie, which is basically used by Facebook to identify different users. We have access cookie and C underscore user cookie, which Facebook uses for authentication purposes. So yeah, we will save it to test.html file, the content that was retrieved, and we will try to open it up into our browser. So yeah, as you can see, the message that I sent, CSP Bypass, has been captured. Fair enough, right?
How do you make the call? Do you make Ajax call, or how do you make cross domain calls? What is the code?
So the code is simply XHR. Basically, we are using XHR.
XML HTTP.
Yeah, XML HTTP request. What we have specifically done in this exploit is we have utilized window.open function. Now, as you can see that the exploit code contains iframe. Now Facebook it uses X-frame options, which prevents any other origin from basically loading into an iframe. We basically modified the same exploit along with basically we have to add something with when we are basically working with Metasploit module. John Phoenix was expert into it. So I basically prepared a basic proof of concept and we utilized window.open function. Since of course there is no such method that, as to the best of my knowledge, which can prevent a website from opening another website via window.open function. So since we use window.open function, X-frame options is bypassed. So even if someone thinks that using X-frame options with your website would basically prevent a Symbolian policy bypass, in 80% of the cases, X-frame options can be replaced with window.open function in order to execute JavaScript independently. So different browsers were infected with this vulnerability. We have UC browser, CM browser, and X1 browser. Of course, you might have not used these browsers, but if you take a look at their Play Store stats, they are very popular, especially in Asia, because all of them have their own selling point. So yeah, this vulnerability, when I reported this vulnerability, Google did not pay attention to it. Google said that we are unable to reproduce this issue on Nexus, which is Google's own product, and it is possible that the OEM, original equipment manufacturer, might have modified the code in the browser which have triggered the vulnerability. Yeah. So they said that they are unable to reproduce this vulnerability. I said, fine, okay, I'll go and publish it. So I published this on my blog. And from my blog, what happened was that the Metasploit team came across my blog somehow. And basically they published, and then Joe Phoenix contacted me and we basically wrote a proof of concept with Metasploit. We basically constructed the Metasploit module that I just demonstrated. And then as of course Metasploit and Pit7 team has a bigger reach, of course, since they are a big company, and Metasploit is something that everyone into this field of information security knows. He is an expert at Metasploit. So widespread Android vulnerability, apparently disaster claim researchers. So yeah, as soon as Metasploit team released it on their blog post, Forbes, Wall Street Journal, BBC started highlighting it. So when they started highlighting it, of course they contacted Google security team and they said that a vulnerability that affects 70% of all of your traffic, and you are saying it's not a vulnerability, it's a vulnerability in the OEM, and we have successfully reproduced it on the Nexus, and your Android guys are not able to reproduce a single vulnerability with few lines of JavaScript code. So yeah, so the response came that after conducting research, we were able to reproduce this. And now we are working internally on a suitable fix. I said, where is my bounty? I said, give me my bounty. They said, okay, since you have released it, no bounty for you. I said, you said that we are not able to reproduce it. When I launched it, released it on my blog, and you were saying you were able to reproduce it. When I asked for bounty, you say that you are not able to give bounty because I violated one of your policies by publicly disclosing the bug. So yeah, this was also covered in Forbes. I sent them a copy of their emails. Deal with it. So yeah, then the guys from Trend Micro, they modified my exploit. And as per the research, 42% of the top 100 browser apps with name browser were vulnerable from Play Store. Now what happens is that that if someone writes a vulnerable code, it gets copied everywhere. So for example, if there is a vulnerability in jQuery, jQuery is being utilized by millions of websites. If there is a vulnerability, DOM-based access vulnerability in jQuery, which means that every single website utilizing that JavaScript would be vulnerable. This is the same case over here. The same old WebView code that was vulnerable to Symbolian policy bypass is being used across different browsers, because nowadays creating a browser is not an issue. All you have to do is you have to basically forward. Okay. So it's similar to the fact that the guys from Backtrack and offensive security, I have huge respect for these guys because they have contributed a lot to the community. But the fact is that they have not developed an operating system. What they have done is they have took an operating system, Debian, and basically they have added their tools and dependency to make life easier for you. So they have not created their operating system. The similar is the case with them. A lot of browser vendors, they do not have resources to basically create a browser. But the problem is that they cannot keep with fixes. So Google is basically paying every month. Google is paying like $70,000 to $80,000 in order to as a payout for their bug bounty program for the Chromium. And imagine, $80,000 per month. This is the budget that no other, I don't think that no other XYZ vendor can afford. Firefox can afford, Chrome can afford, Internet Explorer may be able to afford, because of course it has Microsoft, but a lot of vendors, Maxton browser, CM browser, they are basically small, I don't know about the size, but of course a lot of them are not of size of Microsoft, right? And as a result of this, they basically try to fork the code. They take Chrome and they basically add different features. And then they release it to the market. Now when they release it to the market, a vulnerability found in Chrome is gets fixed. But the same patch cannot be applied over here because now they have modified the code. And they have to see if the patch works or not across all the devices. So these are one of the challenges. So we had this White Hat. White Hat is a very famous company. They do a lot of pen tests and even here in UAE. They have a lot of different very good resources such as Robert R. Snake, which is basically he's a person who created the first access filter evasion cheat sheet. But they tried this. Even they tried to create their own browser. They basically took fork of Chrome and then basically they modified it as per their needs. What happened was that within 24 hours of its release, Travis on Monday found multiple remote code executions in their browser. And then they stopped the calling. So this is what happens. Yeah, this is a special guest star. This is Chrome browser. Now this is the same origin policy. In order to bypass the same origin policy, I think even this guy, where was this guy? Yeah, even Justin Bieber can bypass the same origin policy. You know why? Because it does not implement same origin policy at all. It has modified the code, and researchers found that it does not implement same origin policy bypass, same origin policy at all. Which means that any script present on any origin can by default access any origin. And this was found by Travis Ormond, who is one of the Google's very reputable researchers. Now this was a case where a same origin policy bypass can be elevated and escalated to a remote code execution vulnerability. What happened was that play.google.com, it did implement extreme options. It did implement extreme options, which means that no other website can frame that play.google.com. If you try to frame play.google.com, you will not be able to. But what happened was that if we send a long string of characters, it would trigger a 430 error response. And when you try to frame it within that error response, it would be framed. So since that origin, that website is framed, a universal access or same origin policy bypass means that it can access everything that is present inside the frame. So Google Play has this remote installation feature. This was introduced whereby you can basically link phone to your computer and then basically use Google Play's web application to basically install any application. Now what happens is that since this is web application, right? This is present at play.google.com. This means that if an attacker has found universal access or a same origin policy bypass, this means that he can simulate these clicks with JavaScript. With JavaScript, basically you can completely access the DOM. Since you can access the DOM, you can simulate the clicks as well. So for instance, if I have uploaded one of my malware at play.google.com, and all I would do is basically send someone a link, as soon as he clicks the link, basically the code would simply simulate the clicks and install my malware directly onto the phone. So this was one of the instances where same model policy bypass was escalated to no-code execution vulnerability. So yeah, let's now talk about another class of vulnerability. I know this is very tough, but this is cross-scheme data exposure. This is a term that I personally coined. Not that similar class of vulnerabilities were not found in past, but the fact that there was no official term to define this vulnerability. So you know that our browser can access local files. So, and considering that we are running Linux operating system, we can try to basically access et/password the file scheme. This is the scheme. So as per same policy, a scheme HTTP cannot access contents in file scheme, right? So when we try to load it into an iframe, ideally it should be displayed, but as you can see that Chrome said that not allowed, you're not allowed to load local resource. So I found that in Android stock browser, what you do was that you create a hyperlink and you set the href property to file etc/password. And basically as soon as you right click onto it and click on open in a new window, it would simply open the local file in the new window. Here. So I came up with an attack plan. I said let's exploit it. So I know that if I force a download, it is basically saved into, if SD card is available, it is saved into SD card/download/exploit/the file name. If I can force a download. So this was where the proof of concept was posted. As soon as you visit this link, it would basically force a download. And this download would be then opened by victim. He would right click it and open it into a new tab. And what this exploit.html code would do, it would basically read other files present on the local system and basically send it back to the attacker. I do have a video, but no on coming slides. Yeah. So as soon as the user visits this page, a download is forced, and then when you right click and open this exploit.html into a new window, and since this would open locally, so locally they can access each other since they are on the same origin. So you can basically modify exploit.html to basically retrieve all the content locally and then send it back to the attacker. This was the proof of concept, but this only worked with Gingerbread. And as you know that we only have 3% of users, 3% of the rich users using Android Gingerbread. So the exploit is very simple. What we do is this is the content of exploit.html. So yeah, another attack was using a similar concept was browser cookie cap attack. So since this exploit did not work in modern browsers, we had to come up with a new exploit. So the exploit was very simple. As you can see that what this code does is it simply sets your document.cookie to x equal to script JavaScript. It simply sets your document.cookie to value x, and x is equal to this JavaScript. Now all the browsers, of course, they save their cookie values into different files, which is basically located under data/databases and webview cookies.chrome.db. So the idea was to force this cookie onto victim's browser. So this cookie is now set onto the victim browser, and then ask victim to browse this file locally by utilizing that same exploit. As soon as victim browses this webview cookies.chrome.db file, the JavaScript would be executed under the context of this file, and all the cookies, including HTTP only cookies, would be retrieved easily. Now I do have a live demo because I know this attack is very very complicated. Even to explain this attack. So simply we run this module, and as soon as the victim visits this link, so he would be asked to, now what this page does is it sets the cookie, X cookie to script, and then we compel the victim to open this file into a new tab. Now as soon as he opens this file, now this file basically contains all the cookies. The JavaScript, the cookies that were saved, that included the JavaScript, were basically executed under this context, which means that we were able to retrieve all the cookies. So yeah, then what they did was that instead of loading it into the browser, they basically constructed this HTML viewer. So any file that was downloaded was loaded into this HTML viewer, which did not execute any JavaScript. Yeah, address bar spoofing. Now, address bar spoofing, unlike symbolic policy, cross-key data exposure, and browser cookie capture attacks, are very simple to understand. It's the fact that every single one of us trusts the browser that it's displaying the right URL, right? And Google themselves say that we recognize that address bar is the only reliable security indicator in the modern browsers. It is the only reliable security indicator in modern browsers that can be relied upon, that we can rely upon, that our address bar is not lying. If it says gmail.com, it is really gmail.com. But what if I can trick, what if I can spoof address bar? The address bar looks gmail.com and the content also looks gmail.com. What will you do? There's nothing that we can do, right? It's the trust. Basically, it's the trust that we put into our operating systems, that they are not backdooring us. It's the trust that we put into our browsers. It's basically a game of trust that we have to exploit. So yeah, I would. So this technique is known as initialize and enter. What we do is we basically load Facebook.com into a new window and then basically write it to the new window. Now in the process, browser forgets to update its address bar. So as soon as we open window.open and document.write, the address bar still is facebook.com and the content that we have written is our content that we are able to write. So this means we were able to spoof address bar. This is another address bar spoofing vulnerability that I found. This was found in multiple browsers. Now what happens was that when we browse google.com/psi, it returned to 204 HTTP error code. Now 204 HTTP error code means that no content is displayed. No content is displayed. Now in the process, and then we basically write our HTML to the page. Now in the process, what happens is that the browser preserves, the vulnerability lies in the fact that the browser preserves the content. The browser preserves the address bar. Now I do have a quick demo. Now this was the vulnerability that I found in Facebook. This particular vulnerability was in WordPress application for Android. And as soon as you browse our malicious JavaScript code, what it would do is, click here to redirect. Now as you can see, that the address bar says it's gmail.com. And as you can see that the content is also gmail.com. The content also comes from gmail.com. Now there is no way that one can differentiate between, a normal user can differentiate between a legitimate page and illegitimate page, right? because I think we are running out of time. Before I've written a white paper, which I think you linked, is linked on his website. Yeah, this POC is very simple. So what happens is that, as you can see, that address bar says it's dailymail.co.uk, but this is not actually dailymail.co.uk. So what it is, what happens was that this JavaScript, when it loads in email.com, what it does is basically loads this, it basically sets the URL to the location property, and then basically it says set interval function, and it asks it to reload. It basically updates the location every 10 milliseconds. Now before the browser can get the actual URL, it basically keeps on displaying this, because the interval is very short. It's just like 10 seconds or 10 milliseconds. In 10 milliseconds, the browser keeps updating the URL, which basically prevents browser to update it to the real URL. So the user sees dailymail.co.uk, which instead is email.com. This was Python bug. Basically, it was a bug that I found primarily in Firefox. And as you can see that it says google.com // Arabic. Now the same vulnerability was present in Google Chrome for iOS, Android. It was present in many different browsers. So on the left hand side, so this is the proof of concept. This is simple proof of concept. On the left hand side, you can see Arabic.ml. So we have RTL, right to left characters, and we have left to right. So our English is left to right, right? Left to right. And when we talk about Arabic and Urdu and Persian, it's right to left. So when we place left to right and right to left and left to right, the browser confuses if it's left to right or right to left, right? So, and the browser says it's google.com. The problem with Android is that if you find a vulnerability today in Android, it will take about a year for Samsung, for LG. Of course, Nexus will get fixed easily, right? But not everyone can afford Nexus. So Google is not doing something for poor people; it's only doing for rich people. So in Apple,
They are also doing for rich people.
in Apple, the similar case. But I really like the patch management system, because there is no third party involved in between. So Apple writes the iOS, and the customer simply sends it to the customer, and the customer obtains the updated iOS, and the vulnerabilities are fixed. That's it. Pretty simple, right? And how Android Nexus patch management works for rich people. That says Microsoft is not, PowerPoint is not responding, but it says here. Yeah, so how Android Nexus patch management works. So it's simple. Google writes the iOS and the customer obtains the update, because there is no other person involved in between. But what about everything else? How everything else works in Android? You have LG Mobile, you have mobile from Samsung, you have from BlackBerry or from anyone. What happens is that Google writes the iOS. The iOS is then basically shipped to, operating system is basically then shipped to phone manufacturer. It then modifies the update, because they don't want it to crash. They don't want the patch to crash, right? Because it's going to be applied to millions of devices, right? It then sends it to wireless provider. It then customizes the already customized. It then double customizes the already customized. And then the customer obtains. Wireless provider, AT&T and different wireless providers, because basically they have to push it through wireless providers. So see, I'm LG. Now I have created an update, right? But I have to push it through the subscribers. So I would basically send it to wireless provider. The wireless provider would then basically customize my update to see if it fits in, and then it would send it to the customer. So now the problem is that this is not the only problem. The problem is that a lot of users, but a very tiny part of users, basically have an Android phone which is not subject to updates. And of course, if you see that someone, a Chinese company, they build a $100 phone, and then when they know that in order to keep it with the updates, they have to spend like $50 per device in order to keep the device updated, they would not, because of course security is not the selling point for these devices, right? Very, even less than 0.1% of us buy a phone for its security features, right? So yeah, so if you are using Android, I think you should be using Nexus. You are not using Nexus, because I do a lot of experimenting. Otherwise, you can use iPhone. I mean, no marketing intended, but you can use iPhone. Thank you very much. I would appreciate it.